think it's important to first, even before I talk about the topic, some motivation I think is important. That would be the first part of my talk, would be more about introduction. And then is because you might not be familiar, I know that you're familiar with gravity, and at least at this level I'm going to talk, and with SYK model, but more like the motivation to study these models, which is very much related to the concept of universality and quantum chaos. Since this is something that early in my career I was working, I always like to give my talk some introduction of why really I'm working on these problems and why these problems I think they are relevant. Then the second part of my talk will be more about recent research, though also the first part I will mention some of my previous research on SYK, but the main part of the talk would be about the relation between SYK models and quantum gravitational wormholes. So I will discuss first the traversal wormholes that I didn't do any seminar contribution. It was Maldacena and Chi. And then I will talk about two types of wormholes that I have been working recently, that they are Euclidean, and tell these wormholes and what is the relation with the dynamics of strongly interacting systems, both dissipative and closed systems. So let me start with the introduction, which it has to do with the concept of universality in physics, because it's something that I'm going to use. I need to define. So sometimes when you have a problem which is very complicated, like QCD or nuclei or some aspect of strongly correlated systems, or maybe quantum gravity, you want to find, instead of solving directly a Hamiltonian that in some cases you don't even know, or you know the Hamiltonian but you don't know how to solve it, like happening in condensed matter with the Haber model, or in gravity you may have a model that you think is right, but you have problem to compare with the model. Instead of that, you may find another way to search for universal features of the dynamics. So that means that you said, I don't care about the Hamiltonian, I don't care about my Hamiltonian much, I care a little bit in the way that I will explain, but what I care is about identifying universal features of this motion. So even though it might be that I don't know how to solve QCD, I don't know how to solve the nuclei, it could be that some of these features that I'm going to identify in some effective models, they are universal. So it will appear in QCD or in the nuclei in a certain limit. So then the research is how to identify this limit. So in order to be more precise, let me also say what is universality that I want to introduce. It is first, let me introduce what is not, because there is another concept of universality that is usually is used quite commonly in theoretical physics that is not really related to what I'm doing. So first, let me define that. So first, universality is a bit too misleading name because it can be used with different contexts. So in other contexts, is used to refer to features of the system that they are close to some critical point. What I show here is some sort of general phase diagram for cuprates, and that you see that close a system close to a funnel at low temperature, it could develop some universal features that have to do with correlation functions that it could be described by some form of conformal field theory. And then instead of studying the system that you start with, you can use some general techniques of conformal field theory to describe your system. This is not a universality I'm discussing because my universality that is related to quantum chaos has to do with long time distance and is not related to any conformal field theory, at least not directly related, like this type of criticality proposal that tell you that certain systems, when they are still interacting, they move to some critical regime that can be is universal, that does not depend on the details of the system. So the universality that I'm going to discuss in this talk, or I'm mostly interested, is that related to quantum chaos or related to the random matrix theory. So the way to see that is more to say that my Hamiltonian, I'm not assuming that my Hamiltonian has some specific features like conformal symmetry or something like that. What I'm saying is that for sufficiently long times, the system relaxed to some region in which is only controlled by symmetry. So it does not depend on the detail of the system, but only by symmetries, global symmetries of the system. So you can call this some quantum ergodicity limit, in which dynamic might not be important, but what are only important is symmetry. The fact that dynamic is not important doesn't mean that dynamic is trivial. What it means is that it's controlled by other features, not by the details of the Hamiltonian. This is closely related. So for this to happen, what we need is to have quantum chaos. So now what I'm going to say is to define what I mean by quantum chaos. First, in very simple system, and now in gravity. So quantum chaos means that it's just a quantum mechanics of systems which are classically chaotic. I will define classically chaotic, but what is important about these quantum chaotic systems is that they are universal in the sense that all quantum chaotic systems, in the way that I'm going to define, they behave very similar. So no matter whether they are interacting or they are single particle, for long times, just because they are chaotic, quantum chaotic, they have a very similar behavior. So I always like to cite this is the starting of the novel Anna Karenina of Tolstoy, that said that all happy families are alike, and each unhappy family is unhappy in its own way. So that means that in this context means that all systems which are quantum chaotic, they can have very different Hamiltonian, but in certain range of times, there are features that define them universally. However, each system which is not quantum chaotic is completely different. So you have some spin change that is integrable, is completely unrelated to another spin change with another features, which is also integrable. It's going to be controlled by completely different properties. So to be more precise, so let me just define what is classical chaos. Of course, this is something that you most of you know, or of course all of you know. I just want to say this is very old subject. So paper by Lyapunov and Hadamard, they are even from the 19th century. And has to do classical chaos has to do with sensitivity to initial conditions. So that means you start with two initial conditions very close, you wait, and then even though the initial conditions are very similar, for long times is very different. They increase exponentially. That when the development of computers, they become popular through the 60s, and then you have this name of butterfly effects, that small effects like the effect of a butterfly on air could make the difference between just see a hurricane in the Atlantic or not see a hurricane in the Atlantic. So just as a joke, not joke, but true, that Lorentz first called seagull effect, no butterfly effect. But then he changed. He said the seagull is very ugly animal, so better call it butterfly. Even it's smaller, so it's more spectacular. If you want to see that small effect in local place can have a big effect in the whole dynamic of the system. But what I'm interested in here is in quantum chaos. So quantum chaos, I said, they are the properties of systems which are classically chaotic, quantum properties of systems which are classically chaotic. So this is basically driven by what is called Boigas-Giannoni-Smith conjecture. So this is Oriol that passed away a few years ago. I met him when I was a postdoc in his group in Paris. He made this conjecture in 1984 that say that if you have a system that is quantum chaotic, the spectral correlation, so the spectrum, you compute the spectrum of the Hamiltonian or the relevant operator, usually the Hamiltonian, then you get random matrix theory. So then the question is, what is random matrix theory? So what I mean, you get random matrix theory, I meant that you take your system that is chaotic, can be any system which is classically chaotic, you compute the spectrum of the system, you compute the correlation in the spectrum. So let's say if I have one eigenvalue here, what is the probability of having another eigenvalue here? And then you compare this result with the result of a random matrix. A random matrix is that you replace your Hamiltonian by a matrix, which is, let's say, a matrix representation of the operator, which is random, means that each element, not that the spectrum is random, but each element of the matrix is random and it has some symmetry. It can be Hermitian, but it can be symmetric, or it can be quaternionic. So these matrices, if they are random, they have some correlations. in the eigenvalue in the entry. Then you diagonalize, you get the spectrum. And what they found is that, as you see here, that is what is called the Sinae billiard. Is just one particle. It's very simple system. It's one particle in this with these infinite boundary conditions. And what they found that the spectral correlation are GUE is referred to a system that is a random metric which is chaotic, and they have real entries, symmetric. So the matrix is Hermitian. And then you see agreement with random matrix theory. Actually, what you see here is called the level spacing distribution that gives you the probability of having two eigenvalues at a distance s. So one feature of random matrix is that you have what is called level proportion. So if the eigenvalues, they were random, then you will get Poisson statistics, which is completely different, because Poisson statistic is just exponential. So there is big difference. You can prove that in certain conditions, integral system, not all integral system, that doesn't apply for harmonic oscillators, this spectral correlation is given by Poisson. And however, all systems which are quantum chaotic are given by random matrix. This was a conjecture, which using periodic orbit theory was proved in part. So, you know, all people working in quantum chaos fight. This is a conference of all quantum chaos. They fight whether the proof is a proof or it's not a proof, or it's based on some assumptions. But really, using periodic orbit theory, you get some sense that actually is true. It's true. Of course, when I say is to see that, we need to go to long times. So that means in this context that I compare spectral correlation which are close of eigenvalues which are close to each other. Otherwise, you won't see any agreement, because then the dynamic is not universal. So you prepare a system, the system evolves. When the system, the time evolution is sufficiently long, that means that it's completely universal. So the system, because of this chaos, has lost all memory and behaved in a very similar way. Actually, this idea of introducing random metrics is due to Wegener in the 60s, fighting to describe the nuclei. So, you know, your class, in your course in nuclear study the shared model, but then of course real systems, they have many excitations, these nuclei. And then he wants to understand better this. And then he comes to the conclusion that the only way to understand that is, instead of proposing the nuclear Hamiltonian, solving the Hamiltonian, that was too complicated. He said that if he assumed that he has a random matrix, he found good agreement between the prediction of random matrix and experimental values of this level spacing distribution that give the probability of having two eigenvalues at a distance s. So even though this looks random, it's not random, because the two eigenvalues, for instance, they never tend to be very close, or it's not very likely that they are very close. Now, repulsion, one of the properties of a random spectrum. The other that is called spectral rigidity. The one that now you are maybe more familiar, people doing gravity or doing this type of new things is more familiar. So let me go over this. So what is this spectral rigidity? So that means that if you have eigenvalues, so if the spectrum is given by random metric, it's not enough that the eigenvalues are close to each other. There is less probability to find eigenvalues which are very close. Is that the eigenvalues, they are strongly correlated at long distance. So that means that if you take some eigenvalues and you count the number of eigenvalues in one interval, the fluctuation of this number as you move through the spectrum only grow like a logarithm. So this is called the number variance. And this logarithmics is also a universal feature. If you take the Fourier transform of this, you get the spectral factor that now is very popular. So Masaki-san, in the context of SYK, was one of the authors. So this is from this paper that introduced this, what is called the round, is related to this feature of spectral rigidity that is considered to be universal in the context of quantum chaos. In the context of systems which are quantum chaotic. And it's related to the fact that spectral correlations they have a power law tail. So that means that eigenvalues which are even far away because of this quantum chaos, still they are strongly correlated, which give this rank. This in the history of quantum chaos has had many applications. I mean, from people working in disordered systems, both with interaction or without interactions, working in non-random systems, just quantum chaotic, but not with a random component. And also in the context of QCD, of the Dirac operator in the field of gauge fields, also it was found that it has also this random matrix behavior, which put QCD in the same universality, could be described, certain aspect of QCD, not QCD, but certain aspect of QCD could be described by technique of random matrix. And for this talk, it's important that even in the 70s, people working in nuclear physics, they start working with models that they were not random matrix, but they have infinite range interactions. They were called K-body random ensembles as a toy model for the nuclei. And they also show that these models, they also have this type of random matrix behavior. So they were also quantum chaos. So there is another way. So far I have said that if you have quantum chaos, one way to see quantum chaos is looking at the spectrum and showing that the spectrum is given by okay, so we were discussing this issue of the ramp, and that is one feature of universality, also of quantum chaos. I was saying that there was another window of universality that happened when you have when you compute certain correlation function. This is a short time. It's called, in the context of gravity, scrambling time. So yes. This was introduced a long time ago by Larkin in the 70s, even before this conjecture by Boigas. So it tells you that if you compute certain correlations, so now this correlation, they are called autocorrelations. They are given by using some exponential growth of this correlation. Physically, I prefer to see this correlation like the commutator, the square of commutator of operators, like the one that I'm showing in the upper part of the slide. So what you see here is that there is a time which is called Ehrenfest time in the context of quantum chaos, a scrambling time, that you see an exponential growth of this correlation function. So this exponential growth is controlled by the classical Lyapunov exponent. So that means that this is that's a semi-classical calculation that you can do in simpler systems. So Larkin did in a particle in a random potential. So it means that the quantum uncertainty, there is a time that if you start with system which is classical, start to grow exponentially. And that's a feature of quantum chaos, because for quantum chaos, this is exponential. However, for systems which are non-quantum chaotic, they only grow like power law. So that means that chaos make quantum corrections to grow much faster, grow exponentially. So now, then the question is, what this has to do with quantum gravity at all? Actually, the relation with quantum gravity, that was first done in a kind of hand-waving way by Susskind and Sekino, also Hayden and Preskill, like almost 15 years ago. And basically what they said is that if you place some charge close to a horizon, and then you just leave to just drop it there, you can compute what is the time in which, let's say, the charge covered the horizon. And then you find that that is very fast. So it's logarithmic with the number of degree of freedom of your system. So it's, let's say, logarithmic of h bar or logarithmic of m. And they call this scrambling time. So this has to do with the Riller geometry that close to the horizon, the Riller geometry. You is sort of universal feature, and tell you that in gravity, gravitational systems tend to scramble information very fast. So it's not power law, but it's logarithmic. This time scale in which you see these quantum corrections. And so now can you hear me well, right?
Yes, I can hear you better.
Okay, and then I should not switch on video. So it's okay like that,
right?
Yes,
it's okay. Yeah.
Okay. Then what I want to say is that, so this was some sort of hand-waving ideas that has some impact. But then it came a major result in the 2015, and by Mallasena, Schenker, and Stanford, that is quite spectacular. So what they said is that if you compute this type of correlation function that I told you, okay, so what they found was something quite spectacular, is that, or they claimed there was a demonstration. They said that if you compute a certain out-of-time correlation function, you have to do some normalization in a thermal loop, but they found that there is a universal bound for this exponential graph. So it's not only that what they found is that first, this correlation function, they grow exponentially in the same range that this quantum chaotic grow exponentially. And they did the calculation in gravity, and specifically, they use actually not gravity, but they use techniques also of analyticity, and they prove that this growth also has a limit. So that means that this Lyapunov exponent, that is just semi-classical, that it can be any number that you like, in thermal systems at finite temperature, it has a bound. But even more, they claim that this bound was saturated for black holes. I mean, in field theories in field theories that they have a gravity dual. So in other words, they said that you pick up a field theory that it has that has gravity dual. You compute this correlation function, and then you should see the saturation. Saturation means that this lambda should be equal to 2 pi kBT h. The problem is that it's actually something difficult to compute in specific systems. That is where Kitaev come into the game. So what he's found was one model, what is now is called SYK model, in which actually you see this saturation. So he could compute this 4-point correlation function is in the limit of low temperature, and he found that this Lyapunov exponent predicted by Mallasena that it should be saturated in system with a gravity dual was saturated in this model that he was discussing. This was, these results were presented in California in 2015. He didn't care to publish it, but now this is what is called SYK model. And so basically, it's a simple model of quantum holography. So you have like Majoranas, and they are random couplings. In the simplest case, I will refer many times to Q. When I say Q equal to 4, means that I have 4 Majoranas, but I could have models with 2 or 3 or 4 or 6. But you need more than 2 Majoranas to see quantum chaos. And they have random couplings, and you are mostly interested in the strong coupling limit, which is the limit of low temperature. So the motivation was to test the Mallasena bound. Always in my talks, since I have a background in quantum chaos, I like to say that, to put in context this model, that that before Kitaev, this model was known to the point, was known for Dirac fermions, and which is technically more challenging. So model with infinite range interaction. This model with infinite range interactions, like this Kitaev model, they were very popular in quantum chaos in the late 80s or 90s. Even there are books, and there are all type of research about thermalization, level statistics. So the main motivation, the main progress, which is very important in Kitaev model, is to simplify and making a model of only Majoranas, not Dirac fermions. That does simplify calculation to the point that actually you can do analytic calculations. The first people that introduced these models, they were French and Boigas, and Won, especially French and Boigas in the 70s. So I like to say that in my talks to give credit. So why this SYK is interesting? So why could this? Because now the question is, if SYK saturate the bound of Mallasena, it should have some gravity dual. So it should be relevant for holography. So why we expect that the SYK model is relevant for holography? So actually, you can expect that this is the case because the green functions they have the system have a conformal symmetry. So conformal symmetry is similar to reparametrization symmetry, which is diffeomorphism invariance. So that means that it has the symmetry of gravity that is in the conformal limit of zero temperature. So we are more interested on what happens when you just turn on finite n and finite t, because it has to do with quantum gravity. Then what you find is that this conformal symmetry is broken to a modular to R symmetry. Then within SYK, what you can prove is that the remaining symmetry after you switch on is this SL2. And you can find what are the Gorston mode for this breaking of symmetry from conformal to SL2, and you get what is called the Schwarzian action. So this action you can quantize exactly, and you can compute the exact spectral density from this Schwarzian action in the low temperature limit, and then you get something that also is consistent with the physics of wormholes. You get exponentially growth. This sine hyperbolic is exponentially growth of low energy excitation. So if you put together this with the fact that you see this saturation of the bound, so this 4-point correlation function, they grow exponentially at the maximum rate possible, then people believe that this is really a model of holography. So it must be related to some, this is a zero-dimensional model, so it should be related, so there is only time, so it should be related to some near ADS2 background. So the low temperature limit of near ADS2. So what is this near ADS2 background? So actually it's called Jacob-Teitelbaum gravity. So it's a model that is near ADS2 because you are working with the classical ADS2 geometry, but there is a dilaton, and the physics is in the dilaton, so close to the boundary, develops some non-trivial dynamics. So the physical boundary is not the geometric boundary, and the physics is precisely in this boundary. So on this gravity side, so if you put this gravity side and you put in the boundary, you bring this to the boundary, what you find is that you get again the same action that for SYK. Also, Schenker and Stanford, sorry, I forgot the reference here, proved that using a shockwave, proved that also there was exponential growth of this type of correlation function. So that means that we can say that SYK is dual in the sense that the low temperature limit, in the low temperature limit is dual to this quantum JT gravity. Quantum, by quantum JT gravity, I mean that this classical Schwarzian action, you can do that, you can compute it.
And now I don't hear you again.
Can you hear me now?
Now, okay, yeah.
Now, okay. And I don't know, maybe I can change the network, and let's see if with the network. Can you hear me now?
Yes.
Okay, so let's try with this network. So okay, so and so this just finished the introduction. So what I have introduced is that SYK is a toy model for quantum gravity, and also it seems that it has a property of quantum chaos, because I said that this exponential growth of out-of-time correlation function is related to quantum chaos, or is typical of quantum chaotic systems, because Maldacena bound of Lyapunov exponent, the relevance of this bound is related to the fact that actually points that quantum gravity, quantum chaos could be relevant to quantum gravity, because you could also see this exponential growth in gravitational systems. Now, let me just say very briefly some of my contributions, early contributions of to this relation between SYK and random matrix. So the main contribution, one of the main, was to say that, well, I said that quantum chaos, there are two features of quantum chaos. One is the exponential growth of certain out-of-time correlation function that is controlled by the scrambling time, which is a short time scale. But in the first part of my talk, I said that random matrix is another typical feature of quantum chaos. So it was natural to test whether random matrix is in SYK. So whether the correlation, the spectral correlation of SYK are related to random matrix. Also, in random matrix, I said that the correlation do not depend on the Hamiltonian, but depend on symmetry. So there are different universality classes. So depending on global symmetries, you can identify universality classes. And actually, we will see that in SYK, we have also different universality classes by changing the number of Majoranas and the Q, which count how many Majoranas you have in your Hamiltonian. You can see different universality classes. So tell you how different quantum dynamic can develop in the long time limit. And also, of course, another feature is whether, though this is I'm not going to discuss directly here, whether random matrix is a feature of quantum gravity. I have a paper with one of my postdoc, and also there is this famous paper by Sada and Stanford. I'm not going to discuss that. So let me focus on this first, on the relation of random matrix and SYK and first. So first is, as I said, that SYK, depending on the value of n and the value of q, it has different universality classes. So for instance, it could be that the Hamiltonian is not time reversal invariant, or is time reversal invariant, or is time reversal invariant, but there is some sort of breaking of you have some sort of spin orbit coupling effectively, or you can have chiral symmetry that also belong to a different universality classes. So it was found before my papers in 2016 by Ludwig and Yu that you could define different, depending on the number of Majoranas, you can define different universality classes. So that means that define in how many ways a quantum system, many body chaotic system can become ergodic. And before I give you some example of that, also another thing we did is just explicitly for q equal to 4, find some approximate formula that show this exponential growth that it was later proved like exact results of the theory. And for q equal to 4, we found some approximate results that also show that SYK has this exponential growth of density correlation, which is something that you also see in conformal field theory. This is what is called Cardi formula. Or also you see in the nuclear interaction, this exponential growth of low energy excitation. So that is considered a landmark of quantum black hole features. Now, going back to the issue of universality, first we check that actually you see the agreement between random matrix and SYK is very good. You see in this plot, the PS and the dots, they are SYK for different universality classes. And you see that the agreement, there is no free parameters here. And even the tail of the distribution is very well described by SYK. So that tells you that SYK approach ergodicity very fast, because the prediction of random matrix, they are extremely good. They are extremely good. And more specifically, actually, by working with models with different Q, for instance, we were working in this model introduced by Maldacena and Sachdev with 3 Majoranas. This is a supercharge. We can identify more the universality classes. For instance, we can identify all systems with chiral symmetry. So I don't want to go into details, just to say that the SYK model can be considered as a toy model to reproduce most or all universality classes that you can find in the universal, the classification proposed by Adler and Zimbauer that has 10 universality classes. All of them can find in the context of SYK. This is for SYK. This is for SYK, Hermitian SYK. And but actually, that can be extended even when SYK is non-Hermitian. So that is described open or dissipative quantum chaotic systems. So the way that you make this non-Hermitian is that you put the couplings that they are real, this coupling J, I, K, L, you just make it complex. So that means that you have J plus IM. And we did that. And then we found this paper just published, was published a few months ago. And then we find that we can identify at least half of the total 38 universality classes that they were recently found by Ueda Sensei in Tokyo and his group. Well, I don't know if it's his group or only his group or other people. Now I don't remember all the authors that define in how many ways what are the global symmetries of generic non-Hermitian universality classes. So that means that if we extend SYK to to complex coupling, we can get many other universality classes. So let me just very briefly mention how this works here. So in the context of SYK means that when you have to identify operators that whether you have certain anti-unitary or unitary symmetries. The unitary are called chiral symmetries, or this time reversal related to anti-unitary operators are related to the breaking or not breaking of time reversal invariant or particle Hall symmetry. Particle Hall symmetry simply means that when you do a anti-unitary transformation, the Hamiltonian go to minus the Hamiltonian, which physically means that positive energies, particles that they have positive energies become holes that have negative, and the opposite. In the context of non-Hermitian systems, what you have additionally is that you have systems that you can define operators that what they do, they just take their join to the matrix, and that you don't have this type of symmetry in the Hermitian systems. And this is what makes you get more universality classes. So for Hermitian system, you get 10, and here you get almost 38. So in the context of SYK, the operators that they generate these symmetries, these are, you can call it generalized charge conjugation operators and chiral operators, because for instance, this S that I define is what, if you are familiar with QCDs, is a gamma 5 operator, and so they are this is the one that you use to label all the symmetry classes. So that is very technical, so I don't want to spend much time because still this is part of my introduction. So I just want to say that there is some relation when we apply these operators to this non-Hermitian SYK, depending on Q and depending on N, as you see, we are going to get some symmetries or lack of these symmetries in this in SYK with complex coupling. So the outcome of that is that when we apply these symmetries, we get effectively a Hamiltonian of SYK that have different structures. So in ultimately the way that you see these symmetries is because you get in the matrix realization. So you get the SYK or the model that you are discussing, they get a specific block structure. So the symbol T that you see here is just the transpose without conjugation. And so depending on these symmetries, you get different, whether it's invariant and under this transformation, you get different universality classes. So in SYK, this is labeled. And so let me just go over this. So this is labeled, as you see here, by two things: by the number of interacting Majoranas and by the number of Majoranas n in your systems. So then what we found is that you can first reproduce the 10 universality classes that they are from Hermitian systems. When they are promoted to non-Hermitian, they appear in SYK. And also by using a block structure of SYK, so when you see this anti-diagonal means that you have H and H prime, they could be Hermitian SYK or non-Hermitian SYK, we could identify another 8 universality classes. So the conclusion of that is that SYK is actually you can reproduce most of the universality classes. Now the next question you could ask is whether also is described by random matrix. So can we say that this non-Hermitian SYK is quantum chaotic? So the answer is positive. What you see here is the complex spacing ratio. So basically, what you see these half-eaten donuts is they are given by the distance, the spectral distance, Euclidean distance of this non-Hermitian. So you take this non-Hermitian SYK, you get the spectrum, and then you compute this lambda k, and you see a big difference when q equal to 2, the system is chaotic, is integrable, so you don't see any structure. And then when q is larger than 2, you see these half-eaten donuts, which is a signature in non-Hermitian systems of quantum chaos, or is the prediction of random matrix. So if I take a random matrix, I will get very similar results. If we, of course, to explicit comparison, that is a 2-dimension, is not very good. So we can compute the angular and the radial direction, and then see how good is the prediction of random matrix. Then you see in the top left is for q equal to 2, and the solid line is the prediction of Poisson statistics, and in the others refer to different for q equal to 4, that is quantum chaotic. Then you see very different values of n in SYK that give different universality classes. And then you can see that the agreement actually is excellent, is really excellent, and there is no free parameters. So, I put there different universality classes just to give you an idea that how precise is the spectral calculation, to tell you that SYK agrees with the prediction of random matrices. That is for angular. Also, we can compute the radial. And then you see a very good agreement, quantitative agreement with the prediction of free parameters. And there are no, with the prediction of random matrix without any free parameter. And that goes, even if we go now and compute numbers, we can compute like the variance of these distributions. And then we see that what you see in the lower plot is a prediction of random matrix, and then the dots are the calculation of SYK. So basically, they are indistinguishable of the prediction of random matrix. You see some number, some that we can compare with random matrix. So the conclusion was that we can use SYK to study non-Hermitian systems, and they are going to be ergodic. The ergodic limit of this SYK limit of this, the dynamics is going to be controlled by random matrix theory. So that means that we can use SYK not only for quantum chaos of Hermitian systems, but also quantum chaos of non-Hermitian systems. So that is other results for more universality classes. But I think the idea is that there is some excellent agreement with SYK. So somehow all what we said about Hermitian, it seems that SYK can also be applied for non-Hermitian systems. So non-Hermitian means dissipative open system. So the problems that still remain is that we have identified half of the universality classes, but there are more. And also about relation to quantum gravity of this configuration, just wait, this is what I'm going to talk now. So in a more recent paper, we have discussed not only short range correlations, so these complex spacing ratios, they give correlations of short range, I mean, very long times. But even if we go to shorter times, in one paper, we have seen that SYK still is good at describing, let's say, the ramp. Though there is no ramp in the non-unitary case, there is something slightly different. Still, we find good agreement for between random matrix of SYK with for non-Hermitian systems. So basically, the conclusion is that non-Hermitians SYK seems to be a good toy model to describe strongly correlated systems, ergodic, open, dissipative correlated systems. Now, so let's go beyond this, and that is maybe most about my recent research.
May I ask a question?
Yeah.
Yeah,
sure.
You I mean, presented some much numerical data for various non-Hermitian random matrix classes. But so for Q equals 2, 3, 4, and 6, if I remember correctly. But the systems are classified by Q modulo 4 and N modulo 8. Then so so Q equals 2 is I mean solvable, diagonalizable. So
that's Poisson. That's not entering the classification.
Then you use Q equals 6, but is Q equals 5 numerically difficult?
Is Q equal to 3 physical?
Q equals to 5 difficult. I mean, you require much more computational resources than other cases.
You mean Q equal to 6?
Q equals 5. So you didn't present examples of
okay.
Q modulo 4 equals 1.
No, I understand. Sorry. Now I understand. But the truth, I don't know why we don't do Q equal to 5. No, it does not present any. The only thing is that I mean, odd Q are not related to Hamiltonian because they are related to supercharge. So that means that for classification we can do it, but they are actually we're classifying supercharges, no Hamiltonians. So I think Q equal to 5 maybe because there is no new universality classes, but no, technically it is not. Actually, the computation time increases with Q because it takes more time to generate the matrix. Heavily. So the diagonalization is the same. The diagonalization time is the same, but actually what is more for exact diagonalization, larger Q, even Q equal to 6, you see the difference. And but Q equal to 5 is better actually than Q equal to 6 for that.
I see. Okay, so now I'm seeing your tables in your paper, and in the Q equals Q modulo 4 equals 1, the universality classes for Q modulo 4 equals 3 is repeated. Okay. Sorry. Okay. Thank you very much.
Okay. So this is the table. So it's clear now.
Yes. Thank you.
Okay. So now we are going to change gears. So far I talked about only quantum black holes. So basically, gravity configurations that they are related to black holes, and in the low temperature limit, the near extreme black holes are related to the physics of SYK for near ADS2 backgrounds, which is JT gravity. Now, in recent years, there has been a lot of activity also in other type of gravity configuration related to near ADS2, but related to global ADS2, which are related to wormholes, traversal wormholes. So I want to tell you about some research on how this is related to the dynamics of dissipative quantum systems, strongly correlated dissipative quantum systems, these wormholes. But let's start with the beginning, which is this famous paper by Mallasena and Chio of 2018, that what they found is that if you take two SYK, which are identical, actually are identical with real couplings, these are real couplings, actually this is for Q equal to 4, if not, you have to put some additional factor in the right, but let's not discuss this technicality. And what they did is they had a small perturbation between left, a weak perturbation. So this lambda that you see there is very weak. Then they found that this model can be mapped to a model of, in certain limit, the low temperature limit of this model can be written like two Schwarzschild with some coupling, and this limit also appear if you couple two boundaries in a near ADS2 background with global ADS2, which it has the same symmetry. So, and then what they found is that they found solutions to this gravity problem, and also in SYK, that they look like traversable wormholes. Traversable wormholes are like, you can say like highways in which the system has some tunneling between these 2 points that is enhanced by the strong interaction. And in the context of gravity, has the meaning that is some shortcut in the geometry. For many years, this was considered like science fiction. I mean, if you see interstellar movie, so these guys, they go through Jupiter and then they go to some wormholes and then something wonderful happened. Now, there was a paper by Garcia-Garcia and Wall in 2016 that he found that if you are not too, if you had some weak perturbation between these boundaries in gravity, you could get wormhole solutions that don't break any law, because the problem with many of the wormhole solutions before in gravity were that they were not consistent with some law. So you find the wormholes, but they were not consistent with some physical law. So they were not considered physical. But by putting a weak coupling, Gao and Garcia-Garcia found that, yeah, they were completely fine solutions. I think this was the motivation of Mallasena and Chi to start this. So they just put 2SYK and they add this with some weak coupling. And then they get this effective Schwarzschild action. On the gravity side, so they start with global ADS2 and they are looking for a solution. Global ADS2 has two boundaries and they were looking for solutions coupling these two boundaries. And they have some sort of close to T translational invariance of this dilaton that generate the dynamics. So the degree of freedom of the dilatons, they are close to the boundaries, and they try to find solutions in which basically the dilaton is eternal. So it's always moving close to the boundary, which in the field theory correspond to some tunneling channel, enhanced tunneling channel. So in the gravity context, the interaction must be at the level of the boundaries and by a double trace deformations, and then you need many fields. I mean, many fields. You need n ball matter fields to make large enough so it can induce the effect that you want. It's weak in the sense that this G is going to be small, because otherwise you cannot do many. The calculation is not consistent. Because of this, you need to put this when you do the average over the path integral, gravity path integral, you want to replace that by the average over the correlation function. So that this can only happen when the coupling is small, because you can do some resummation of in the gravity calculation. But it's something that I don't want to discuss here. The only thing I want to discuss that in the end, what you get is that this TL and T right represent the physical dilaton that describe the dynamics, the non-trivial dynamics. They found non-trivial solution that they go in these vertical lines, close to these vertical lines. The dotted line that you see are these resummation that you have to do to see these wormhole solutions. What is important for this purpose is that after you do all this, on the gravity side, you get exactly the same action. So, okay, then you say, why this is hot at all? Why getting wormholes is nice? The issue is that it has a very deep meaning also in field theory. That's the point I want to emphasize, that I don't think it's sufficiently emphasized. So what they found, for instance, is that Mallasena and Chi, is that the gap, they found that when they put the left and right together, they found a non-trivial gap developed. Gap developing quantum mechanics when you put things together is tunneling, so that's not surprising. What is very surprising is that the gap they get for Q equal to 4 is lambda to 2/3, has a fractional power. So that means that when lambda is very small, it's much larger than the usual lambda that you get by coupling two things. So that means if I couple two things, I should get in linear, perturbation theory, quantum mechanics, something that is proportional to lambda, or maybe lambda squared if there is some symmetry, but at least should be proportional to lambda. And they found the gap is enhanced. So this gap is what protects the wormhole, the ground state become a wormhole, which is close to a thermofield double state. So it's a highly entangled quantum state. And the gap is enhanced. So that is conceptually, it has to do with the idea that in gravity you get a shortcut. So even though you put some coupling, what you get much more than what you put. So you put some coupling between left and right, and what you get because of the interactions, strong interactions, which which holographically has to do with the gravity interpretation, is that an enhancement of the tunneling, and that is represented by a larger gap. And that is really very interesting. Also, another feature that you observe is a first order phase transition. So you have the Freddy is flat. This is the wormhole phase, and then there is a first order phase transition to a phase with two black holes, and that's normal. So that means I hit the system. So then, as happening in quantum mechanics, so the gap will close because of temperature, and then ultimately what you get are two wormholes coupled by the boundary. So they are two wormholes, and they are coupled by the boundary, not by the horizon. And that is a perturbative calculation, and that is fine. So then you get basically two wormholes for high temperature. But the low temperature is a new state of quantum matter. You can see that also have a very nice gravitational interpretation. So my first contribution to that was to show what was how random matrix enters here. So what we found is that this Hawking phase transition between this wormhole and this on this black hole transition also appears in the spectrum. So we found that low temperature, the low energy excitation, they were not given by random matrix, as you see here. They were intermediate between Poisson and random matrix. And then as we move for high energy excitation that would correspond to the black hole phase, we saw a transition to random matrix behavior. So that means that the black hole, the wormhole, doesn't seem to be described by random matrix behavior. And that was my first contribution. And now what I want to say is also there is another way that you can, well, another way to see it's a different problem. So what happened if you put two SYKs, left and right, but you put you don't put any coupling, so you don't put any explicit coupling left and right, but you make the couplings complex. So sorry, I didn't explain well in the slide that left and right, they are not identical. So one is the complex conjugate of the other. So in other words, the left SYK is have J plus IM, and the right SYK has J minus IM. So then you have PT symmetry. So they are disconnected. So they are not talking each other. They have complex random coupling, which one is complex conjugate of the other. But it's important, they are not connected. So lambda is equal to 0 in this setting. Actually, in some corner of Maldacena and Chi paper, they mentioned that this possibility, and we explored that with first on the field theory side and then on the gravity side. So what we found on the gravity on the field theory side was that actually we could even propose some analytical calculation of the free energy. And surprisingly, what we found was a free energy that was very similar to that of traversable wormholes. So we saw also a flat free energy, and it has a first order phase transition as that observed for in Maldacena and Chi for traversable wormholes. Also, we found that this was not particular to SYK, that could be found also for random matrices. So that means two random matrices with coupling that one was non-Hermitian, one complex conjugate of the other. And then this type of SYK, they also have a gap in the spectrum. But then this gap is proportional to K squared is the strength of the imaginary coupling. So if there is no imaginary coupling, then we have two SYK identical with no coupling, nothing happens. But then if the strength of the imaginary couplings is K squared, so for K equal to 1, real and complex, they are the same, we get a gap in the spectrum that is related to goes like K squared with the strength of the imaginary coupling. But remember, this gap is not a gap in the, I mean, I say gap in the spectrum, it's a gap in the green functions. In other words, if I diagonalize the matrix, this left and right, they don't talk each other. So that means the spectrum has no gap. So you see here the spectrum, I showed here the spectrum, there is no gap. The gap is a consequence of ensemble average or on complex couplings. Of course, this is related to the, yeah.
Excuse me, what is K again? Could you explain what K is again?
You mean J?
K.
K. Sorry, K is the strength. K is the strength of the imaginary coupling. So M.
Okay.
So J and M are random coupling. So let's say the strength is K, is 1 of J.
Yes.
M is K.
Okay.
So it has a strength K. So that means when K is equal to 1, J and M has the same strength.
Okay,
so,
thank you.
So K is the strength of M. So we even though it's K, the gap goes like K squared. But again, this is a gap, but it's not, if you diagonalize, you don't see the gap, because it's a gap that appears in the green functions and in the thermodynamic properties, but it's not a gap because we don't have left-right explicit interaction. Of course, this sounds a lot, if you know gravity, of this problem of factorization. So it's more like it's like a field theory analogous of that, of the problem of factorization in ADS. So that means that you put together two fields, you put two theories, they don't talk each other, and you know that in gravity, if you do that, quantum corrections of this, you can get configuration of wormhole configurations that are problematic because they don't have field theory analogs. So this is a field theory that it may have this type of configurations that they left and right, even though they don't talk each other. In the Hamiltonian, when you do ensemble average with imaginary couplings, they talk each other, and then you see something similar to adding a coupling, explicit coupling between left and right. Actually, I didn't want to go into technical details, but the Schwinger-Gleason equations are very similar of the two models, of Maldacena and Chi of this model. So, and also another important thing is chaos is important. If we repeat the calculation for Q equal to 2.
Question?
Yeah, sure.
So you are getting, even there is no coupling, you are getting the gap because this non-hermiticity, Prof?
Yeah, exactly. For the non-hermiticity and the fact that I have one is the complex conjugate of the other. So I need this. So
okay.
that's the key, the point I want to make. So this is why I have two field theories that they don't talk each other at the level of the Hamiltonian, but when I do ensemble average, they start talking each other. So it's similar to what happened with the wormhole configuration in Euclidean quantum gravity, that when you include quantum corrections, you see these configurations. Even though the two boundaries, initially, the two geometries, they don't talk each other, but they can talk each other after quantum correction. So this is one mechanism in field theory that you could see something similar. And chaos is important. Quantum chaos is important in the sense that if I repeat the calculation for Q equal to 2, I see something qualitatively different. So still I see some transition, but there are like many transitions. So actually, this is the derivative of the free energy. So there are regions in which the free energy has a very bad, has a negative entropy. Sorry, so it's a little bit pathological for Q equal to 2. Q equal to 4 is fine. So now we go to the gravity dual of that. So together with Victor Godet, so what we found that actually this was essentially Euclidean wormhole. So what we did was to study with these results in SYK. So we study a gravity system. So we start with near ADS2 geometry. So we have a dilaton. So we put some matter. So we put some scalar, and then we study what is the dilaton, which is the physical degree of freedom that describes this quantum gravity correction. How the geometry is changed if we start with global ADS2, how change the geometry if we add this scalar. And the trick that we need to put is, so we add this scalar chi, and then we need to introduce non-trivial boundary conditions, so some sort of complex sources by hand, because what we want is to reproduce this double cone geometry. So we want to find that by solving the equations, we want to find something that we can call Euclidean wormhole. So you have like two boundaries, and they are together, they are mixed together with some bottleneck. Unlike, these geometries have been discussed by Stanford and Sad in all these papers about matrix realization of JT gravity, I want to emphasize that in our case, it's different. The configuration is the same, but our B is fixed because this is a solution of the equation of motion. So what they discuss in all this paper by Stanford, these configurations, they are quantum in the sense that they have to compute the moduli space. So they need to integrate over this B. In our case, B is given by a saddle point equation. So they are fixed geometries. The other, basically, they are geometries that they don't solve the equation of motion because they don't have a scalar. So we need a scalar to find solution of the equation of motion. So what they do is they pick up this configuration and they compute all possible values of this configuration. They compute the quantum path integral. But they are no solution of the classical equation of motion of this SAD and Stanford papers. So what we do is it's more specific. So we add a scalar, and then we find then that the classical equation of motion, they have we found solutions that they connect the two boundaries. And
can I ask a question?
Yeah.
Is the saddle point a stable saddle point?
We believe so. I mean, we didn't do. I mean, stability analysis you can do only to some extent, but yeah, we believe that it's a stable saddle point. But it depends what you define as stable.
No, generally the matter effects have this Casimir energy effect, which will.
I mean, if you ask me whether it's stable, I mean, you are not considering the back reaction of the geometry in full extent. So it might be that in that sense, but we did some stability analysis or other perturbations within that we are fixing ADS2 or fix. So we are just computing the dilaton. Okay. So it might be that we do the full gravity calculation, it might not be stable. But in that sense, it's not. But we did some checks of stability.
Okay. Thank you.
Then once we solve the equation of motion, we can compute the free energy. And what you see here is the free energy. And then we see very similar to the SYK. So this black dot is the flat part, that is the one-hole phase. And then there is a very sharp phase, first order phase transition to a two black hole phase. So in other words, in our equations, we find that when we increase temperature, this one-hole solution become subleading. So that means that there are other solutions of the equation of motion that represent two black holes that they are better in the sense that they have lower energy. So they are the one that correspond. So we see very similar physics from the gravity side and from the SYK side. Of course, this is nothing to do, traversable wormhole is a dynamical field. This is not related to tunneling, quantum tunneling. That is a phenomenon in real time. We are now in imaginary time, in Euclidean time. And so it's different kind of transition. So even though, let me be more precise because this is important. I'm not claiming that by doing these tricks of doing ensemble average or replica, off diagonal breaking, I'm not claiming that you can make a left talk to right. It's that there is some sort of synchronization between the two because we are talking about in imaginary, Euclidean time. All these calculations are done in Euclidean time. So this will be important in what I'm going to explain now. That is the first part of the talk, the last part of the talk. So I have already said that wormholes, they are relevant for this Euclidean and traversable wormholes. Now we are going to see more speculative on the gravity side, not on the field theory side, how wormholes also may be relevant for dissipative quantum mechanics. The time evolution of strong interacting dissipative and quantum chaotic matter. So this is a paper that came out last month. There is some overlap with a paper by Ryu Group in Princeton that came out a few days later. And basically, what we want to understand is that we have a SYK, and we couple this SYK to a bath, which is a Lindblad bath. So this type of setting, known as SYK by in ADS CFT, has been discussed. Tadeusz Sanz has a paper with Adolfo del Campo in 2019 that what is the effect of decoherence or have open system in holography. Here, what we are studying is what happens if you couple a SYK to a thermal bath, the real-time evolution. So there were papers in the literature that they were describing like the entanglement entropy. This is something we can do also. Maybe I will do in the future, but what I'm going to discuss here is something simpler. It's more like a retarded Green function. So how a SYK that you couple to environment, how relax to equilibrium. So the setting of the calculation is that we take SYK in a thermal bath, and we have the bath at formally infinite temperature. And then we slightly perturb this, and then study using linear, effectively call this path integral a linear response, how the system approach equilibrium. And then we have found some interesting dualities between these systems at infinite temperature and another system at 0 temperature. And then also we have found that this setting it might have a gravity dual. So at first I want to discuss on the gravity side and why this system, sorry, on the SYK, and how this system might be related to wormhole configurations. So the setting of the system is very simple. So we start with a single site SYK with real couplings. So these J's, they have real couplings. Then we couple this to environment using what is called the Lindblad approach, which is basically assuming that we have a Markovian approach. So that is a cheap approach to describe a bath. So instead of putting this bath degree of freedom explicitly, like let's say with another SYK with Q equal to 2, like there are some papers in the literature. So what we do is we put some Lindblad environment. Lindblad is that we introduce some operators, they couple to the density matrix, and we know that this form that you see in this in the slide give me some Markovian. So it's give me a bath, it has no memory, but the advantage of this bath is that the degree of freedom are the same degree of freedom of my system. So effectively, I'm replacing my Hamiltonian by some Liouvillean, which is non-Hermitian, and that describe the time evolution of the density matrix. So what you see on the right-hand side is nothing but the derivative of the density matrix rho with respect to real time. So that means that instead of studying Hamiltonian, I study some more general operators, but I can do basically the same thing. As I said, we start with a system which is formally, maybe it's a little bit misleading saying that we are working with thermophile double states because we are working with a thermal state at infinite temperature. It will become a thermophile double state when we double the degree of freedom. But first, I will explain that it's just a system that is an infinite temperature. We perturb a little bit, and we want to study how the system approach equilibrium. So what we want to compute is just the retarded Green function. We could compute other things, but the simplest thing is just the retarded Green functions in real time. So it's important that this calculation that I'm going to do. Yeah.
Yeah. So can you go to the previous slide?
Yeah.
So how this choice of these jump operators are important for
this this is a good question.
State?
Yeah, so we choose this operator for simplicity. There were previous papers that they discuss an aspect of this model by Ryu and by one of my collaborators. They use, for instance, these jump operators with two Majoranas, or you can even do with random interactions. So you can put, let's say, instead of this Li, you can sum over some random number times 2 or 3 Majorana operators. To some extent, properties should not depend much on the choice, but certainly that is a free choice. It's a degree of freedom that you have that you can put as you wish. Our motivation to do that is because this is the simplest, and we want to make contact with the previous Malacena and Chi papers and papers with traversable wormholes. So this is why we choose the simplest jump operator. But yes, there is no.
They choose some non-Hermitian jump operators. Then can you choose this infinite temperature state as initial state?
Yeah. In principle, you can choose I think you can choose non-Hermitian operators. Yeah, there you could in principle choose non-Hermitian operators. I think so. I wouldn't tell you that 100% because that's actually was my first paper on Lindblad. But yeah, you have freedom to choose certainly 1 or 2 or 3 jump operator with 2 or 3 Majoranas. Yeah.
I'm afraid because this is a kind of equilibrium steady state, right? In that can, I mean, if you choose some non-Hermitian operators, it might lead to some non-equilibrium steady state.
No, okay, okay. Let me be more precise. If you choose the problem is that when I say in this slide that my final state is going to be an infinite temperature thermofillable state, that depends on my choice of jump operator. If I choose an exotic jump operator, then I need first to find out what is my final state. Because then it might be that it's maybe a thermal state at finite temperature. So then you can prove this easily. I'm not going to present the calculation, but you can prove that the final state or in this setting can be one of the solutions in this infinite temperature state. So this is one of the reasons. What I know is that if you do some Hermitian operator with more Majoranas, still you will get this final state, which will be infinite temperature state. But if you choose other type of jump operators, you may get other type of steady states. Maybe it's even not thermofillable. You could get other type of configurations. Yeah.
Okay. Thank you very much.
Okay. So now what is interesting here, because then you will see why the wormhole physics enters, is that we want to do simple calculation. This has been done in the context of single SYK without coupling. It's in the actually this calculation, not with this formalism, is with the formalism of analytic continuation, is in the paper of Stanford and Maldacena, using analytic continuation to compute retarded green functions in real time in SYK. But let's say the formal way to do that is what is called the Keldysh formalism. So the Keldysh formalism.
Yeah. Excuse me, we are already over 30 minutes late, so I'm afraid that there's not much time. Sorry.
Okay. Then let me, since we have all these problems, I thought I had more time. This is why I didn't stop. Okay. And yeah, but I understand. Okay, so let me just conclude that. And so when we double the degree of freedom, so we get something that is something very close to a wormhole. So we have left, we get right, and then we get something which is a wormhole, but with Hamiltonians that they have imaginary couplings. So these imaginary couplings depend on mu, and then what we see is that the green functions, they decay exponentially with a frequency and with exponent that depend on the coupling. This coupling is the coupling, this mu is the coupling to the environment. So we identify some phase transitions. So we still have a gap, that the gap undergoes phase transitions, and the frequency also, when we add a stronger coupling to the environment, we stop seeing these oscillations. And we can do this analytically by using the large Q. We can get analytic calculations. And again, all these features depend on quantum chaos. If we do Q equal to 2, we see something different. We don't see exponential decay. And finally, the gravity interpretation is that all this SYK with imaginary coupling seems to be related to what is called wormholes in DS geometry, not in ADS geometry. So these are basically this double cone that you inverted. DS geometry is when you have Q equal to, you have a positive cosmological constant, and that basically means that you go from real to imaginary couplings. It seems that these all results for free energy are consistent with those of wormholes in DS geometry. So thank you very much. I'm very sorry for the extended time. So thank you very much.
Thank you very much. So actually, we announced that online coffee break will be held on special chat, but due to the connection problems, let us continue on this Zoom session. But before that, let's thank Antonio again.
Yeah.
So for coming to this colloquium, thank you very much.
Okay. Okay. Thank you. I'm sorry again for all these problems.
No. So let us continue in this session for questions and discussions.
Okay.
So,
can I ask one question? So,
please.
In your approach, the Keldysh wormhole that you just quickly talk, is it a traversable wormhole or is it different than?
No. Okay, that's a good question. We thought about that for a long time. No, I don't think this is the point. Is that they are not traversable wormholes because we are talking about the SY case that we have here. Let me just go and tell more explicitly what are the SY case that we have here. They are SY case with an imaginary coupling. So I don't think that they can hold okay. So this is the SY case. So you see this SY case, they are real, but they have an I in front. This I is important. So that means that they are with imaginary couplings. So I don't think that they could be related to traversal wormholes because, or if they are related, they are traversal wormholes in DS space. It's not in ADS space because we also see a gap. So we see a gap. It's a real time, and if they are related in DS geometry, not in ADS geometry.
Yes, but even in this Euclidean problem, your Hamiltonian, the first and second one, the non-Hermitian, but again you have a coupling, right? In terms of mu. So
yeah.
What is the interpretation of this mu in this Keldysh wormhole? Is the
no the interpretation that is the coupling in the environment. Actually, what physically means is that this left and right in this context has to do with fermions, that they are backward in time and forward in time. So what the coupling to the environment is the connection between the two. So the physical meaning in Keldysh of this mu is the coupling to the environment. However, our properties do not depend much on that. Let me just show you these plots. And so what you see here, for instance, that is the frequency of the oscillations that we see in the green functions. Even for mu equal to 0, we see this oscillation. So let's say the wormhole nature, that seems to be similar, more like to Euclidean wormholes, in the sense that even with no coupling, with mu equal to 0, we see all the interesting physics here. In the sense that it seems that the system approaches equilibrium very fast, and because this mu, even when there is no coupling to the environment, so quantum chaos in this case induce a transition, to the equilibrium state very fast. So in other words, the effect of the environment is not very important here. Is actually what it does is to
even for mu equals to 0.
Yeah,
you have some finite gap that you are
for mu equal to 0, even if the two left and right are not connected at the level of Keldysh, still we see very similar properties.
Okay.
So the physics of mu equal to 0, a small mu, is very similar. So this is what brings me to that more than traversable wormholes is not, there is nothing new when we have mu. Physically, it's not nothing new. So it's more like the physics of Euclidean, in the sense that we have two things that are non-Hermitian, and they are not coupled each other, but develop some coupling after ensemble average. So this is why I think it's physically close to Euclidean. Of course, they are not Euclidean at all because they are in real time. But the physics is closer to Euclidean because it's not that we have a weak coupling and we see something big like in Maldacena and Chi. Is that the mu, you can see here, the mu, let's say the gap, when we have a gap, even when mu is equal to 0. So what the gap does is some sort of perturbative things. Then something happened very strong at mu equal to 15, but that could be a transition maybe to some traversable wormhole phase. But for a small mu, it's very similar to mu equal to 0.
I see. So that means this mu is not like a length of the wormhole, right? Isn't
exactly. That's it. Actually, when we write the paper, we want to say the opposite. We want to say, oh no, mu has a big effect, and then we are studying coupling to the environment has an effect, and maybe it has to do with this information paradox, blah blah. But then we realize that even with no environment, we see the interesting fact is this Keldysh wormhole has to, even if you don't put environment, you see something similar.
Yeah. Okay. Thank you. Thanks very much.
Yeah.
Any other questions?
Excuse me, I have a question.
Please.
Yeah.
Thank you for your talk. I was wondering, when you consider the holographic dual of this kind of open quantum system, is there any problem with memory effects? I mean, like non-Markovianity?
I mean, you mean problem that in our model, by design, we are working with a model that it has is Markovian by design.
You have a many-body strongly correlated system, so you might expect that there's some breaking of, I don't know, if you're using Lindblad equation, maybe there might be a problem with the rotating wave approximation or.
Okay, you mean at this level? Yeah, that could be. Yeah, we didn't consider. Yeah. I now understand your question. Yeah, we didn't consider that. Yeah. Certainly, that is a possibility. Actually, our motivation was basically to study something which is simple enough to do analytic calculations.
Okay.
And because if we go to the other system that people did, that they coupled to other SYKs, then the problem is that we want something that we could understand better. This is why we choose this Lindblad thing. Yeah.
Okay. Thanks.
Yeah.
Okay.
Please. Can I ask one more? So how the physics is important for if you choose this complex fermion instead of this Majorana fermion? Is it really depends?
Sorry, I didn't get your question.
So you have chosen this Majorana fermions, right?
Yeah.
But is it something that you choose if you choose the complex fermions? And
I mean, we choose again Majorana fermions. We follow Kitaev philosophy just because it's simpler. So of course we could repeat exactly the same with Dirac fermions. Whether there is a new physics that will require some thinking, because if you add fermions, if you add Majorana, if you add Dirac fermions, only Dirac fermions, only that, I don't think that is much different. However, if you add charge, so you put a chemical potential, it could be some new physics there. The problem is technically is much more complicated. I mean, technically, not numerically. Numerically is okay, but if you want to do analytic calculations, it's usually a little bit more complicated to do Dirac fermions. So unless you have a motivation to do that, a specific motivation on gravity, or like you want to do charge black holes or charge wormholes, then of course you need to put the Dirac fermion. If not, technically it's more complicated. So usually people prefer Majorana. Actually, this is the big progress of Kitaev, realizing that, okay, with Majoranas, you get the interest in physics.
Okay, thanks.
You mean multiple conserved quantities?
Sorry?
Do you mean more than one conserved quantities? Because I mean, energy is conserved in Hermitian system, but
precisely.
Charge would be conserved if.
The fact that charge is conserved, for instance, even if you compute the spectrum in the other project, if we could do that with Dirac fermions, but then you have the problem that you have conserved charges. You have the charge is conserved, so then you need to know exactly what sector of your Hamiltonian to do a spectral analysis is much more complicated. So the fact that you have conserved quantities makes your calculation more difficult, and that you could have a reason to do that, very good reason, and then you should do it. But if not, it's better to work with Majoranas. Actually, people in quantum chaos were working with these Dirac fermions for many years, and then they stopped because they could not get many more results because it was all numerics. But now there are techniques more developed to do that. But my advice is that if you can do that with fermions, unless you want to study charge, which is very good, nice problem, don't do Dirac fermion, do Majoranas. If you want to study charge, in this problem I'm discussing, you could study what is the effect of finite charge. I think it's an interesting problem to study. Then you have to do Dirac fermions. If not, stick to Majoranas.
Okay. Could you show your conclusions slide again?
Yeah, conclusions.
Because
I don't know. Yeah,
I
just want to finish. Sorry. Usually I'm very careful with time, but with all these problems, now I'm doing that on my telephone. So now in the computer, I have more. The conclusion basically is saying that wormholes play an important role in different parts of physics, not only in gravity. So I think this is worth exploring this type of configurations that not only from the gravity point of view that can solve some problem in long-term problem in gravity, but on the field theory side, that they give you some intuition for new physics. It's like the enhancement of the tunneling that I'm sure that somebody will publish a Nature or Science when they do that in the lab. The enhancement of the gap due to these traversal wormholes is something that you can prove in principle in experiments. It should be a universal quantum effect that you should see.
Okay, thank you.
And also, it should be relevant. Pushing it with more complex model should be. One should be able to make contact with the information paradox. I believe so also, as has been shown in this paper by Maldacena and Stanford 2 or 3 years ago. I think there might be some SYK setting that it could be really reproduce this type of situations related to wormholes.
Okay, so if there are no more questions or comments, no more agenda. Okay, please. Yeah, Mochizuki-san.
Hi, Antonio, nice talk. And my question is, what you said about the transition between the black hole and the two black holes and one wormhole. So you claim, are you claiming that the transition is related to the metal insulator transition between the boson and the matrix? Is that what you're saying?
Well, that is a very strong claim. What actually, the truth, I mean, well, I'm sure about the numerics. I'm sure the results point to that direction. So what we did actually points exactly to that direction. It points that the wormholes and the low energy excitations related to wormholes. So in a larger limit, there is only the wormholes in the ground state, and the rest is already black hole. It's protected. The wormhole is protected by a gap. But if you go to finite M, what you see is that you have the ground state, which is the wormhole, that since it's only one state, you cannot do level statistics. And then you have excitation of the wormhole, that they are gravity. I mean, they are supposed to be related to gravity. And what we found is that these excitations of the wormhole, they look like integrable. They look like Poisson. Yeah, but my experience is that maybe you will need more calculations to be sure about that, because it's complicated in the sense that there are very few eigenvalues. They have this property. So in the moment that you move up in the spectrum, then you get perfect random metrics. So I will need to do some finite scaling analysis to be more careful. But yet the evidence points that wormholes, excitation of wormholes to be precise, because the wormhole itself is just one state. In the larger limit is the ground state. They are like integrable, so they are not quantum chaotic. That is the evidence. Yeah, but it could be that there may be some symmetry that we are missing in the low energy that we need to extract to do the spectral analysis. That also could be. But the evidence that we have is that this excitation of traversal wormhole, yeah, there is some. You can call it metal insulator transition. You can call it, though, I would call it more like integrable chaotic transition.
Okay, thank you.
Do you have any comments on sparse SYK models?
I mean, I didn't have, in all this colloquium. Yeah, the comment is that, well, the comment is, for those that they don't know, the one is possible to study SYK, but removing some links. So that means that instead of working with You can do that Hermitian and non-Hermitian. I think non-Hermitian still has not been published, but so that means that you just remove some links, so then become a sparse SYK.
Yes.
So so if you do that, the advantage is that actually what is surprising is that so is this JIKL. So instead of having infinite range interaction, you just make some of them 0. So then the moment becomes sparse. And what is surprising is that all these properties, all these I mean wormholes and random metrics are very robust. So even though you remove most, I mean, for Q equal to 4, you have n to the 4th couplings that are non-zero, n to the 4th. So even if you remove n, so if you go from n to the 4 to n with a prefactor much bigger than 1, like 4n, you still get similar properties, very similar properties. And it's surprising that this computationally means that maybe you can make your code much faster and go to larger volumes, because larger sizes, because it's very efficient. It seems that such a sparse matrix should be very efficient for numerical calculation.
What do you mean by it is? I mean, for n to the 4 going to n number of couplings?
Mean that, for instance, you take this model. I mean, forget about now 2 sides. Then the JIKL, these are this IJKL, they run from 1 to n, and then you can prove that you have n to the 4th sides are non-zero. So in your metrics, you have a metric which is 2 to n over 2, but you only get n to the 4th with this model that I'm telling you.
Yes.
Couplings which are non-zero. What I'm saying is that if you remove randomly some of these couplings, so you make some of this JIKL equal to 0 by hand, you say with probability something, this coupling is 0, and that's it. In that way, you can reduce the number of couplings from n to the 4th, let's say, to n or to 4n. What I'm saying that even in this very sparse case, the properties of SYK seems to be very similar.
Yeah, I mean, what properties of SYK will be? Do we expect all properties or only low energy spectrum?
No,
properties?
I mean, what we did was level statistics. Because actually the problem is that analytically it's very difficult to deal with this type of sparse model, because you cannot even do large chain calculations. You can do, but there are terms that are difficult to handle. What I'm saying is that what we did was sort of free energy or level spectrum, and the spectrum looked very similar to the one with all couplings.
I see.
And very similar actually, but of course if you push enough, so if you go to sufficiently small couplings, then what you find is that you see deviation. But you get, for instance, very good agreement with random metrics, even though you reduce from n to the 4 to 3n, then you see very good agreement with random metrics.
I mean, my question is, do we find some sort of, this low energy Schwarzschian or the Otok saturation?
I don't know.
Those kinds of things.
I think, okay, that I think nobody knows about that. I think there are not enough, that is doable, even numerically is doable, but I think has not been done yet. Whether that's interesting question. I don't know. I think so, but I don't know. Because that requires a very careful numerical calculation, because you only can do exact diagonalization. Still, there is not developed large chain analysis. There's to do Schwinger-Dyson with sparse is not possible. I think it's not possible, and or in a rigorous way, you can do that more hand waving, just picking up terms you like. No, I think this is not known. So, or let me be more precise. It's not known whether there is a gravitational interpretation of the system.
Okay. Thank you.
Thank you. So it's almost time to also finish the coffee break. Actually, I think this was kind of mixed between discussion part and coffee break. But if there are no, so let us keep in touch, and
of course.
I hope in the future we can, in the very near future, we can meet physically meet
Of course, I look forward to meeting you, Masaki-san, and all of you. And please feel free to contact me if some question arise. I will be happy to discuss with you privately.
Thank you. And also,
okay, thank you very much.
So thank you very much. And
sorry.
Yeah.
Okay,
so sorry. I actually wanted to ask a question. Waiting.
Oh, sorry.
Sorry. Yeah. So sorry. Yeah. But thank you very nice talk, Antonio. And actually, I have a very naive question, maybe just for curiosity. So, can you generalize your no-emission two-side SYK to more than two-side SYK and get the multi-boundary one-fold, Euclidean one-fold?
Sorry, I couldn't understand your question. You said that if I can generate a non-Hermitian SYK with what property?
So now you have two SYK with non-Hermitian J. So one J is complex and the other J is the complex conjugate. So my question is, suppose you have three SYK, then how can you generalize it to complex version, non-Hermitian version, and then so that you can get the for example, for three SYK case, whether you can get three boundary Euclidean one-fold or not.
But sorry, I'm sure that I understand the question. So I start with a non-Hermitian SYK.
Yeah.
And then what was the question is, how can I generate what?
Maybe more than two copies.
Yeah.
More than two. Sorry, more than two. This is what I think. I understand your question now. Yeah. Sorry, I didn't got this more than two. Yeah. The problem, okay, because this is a long-term project, I have to do more than two. The problem is that technically become more complicated because even if you do, this is possible to do. Okay, or let me be more precise. Let me be more precise because it's something I thought about that. For Maldacena and Chi, it's possible. Of course, you can do this with no problem. For Keldysh, I think there is no justification to do more than two because these two come from how you define the path integral in Keldysh. Of course, you can do that by hand. You can put three and study, but then I'm not sure whether you can make a relation with real-time dynamics if you put more than two. But of course, you can study the system. Technically, it's possible to study the system, but become more complicated because the Swinger-Dyson equation, then you get all possible crossing terms. And then basically what you need is an intuition or some effect that you want to study, because it will require additional substantial effort going from 2 to 3. And for this Keldysh thing, I don't know if you can justify that because the two copies here, they come from the path integral. I'm not sure whether you can put more than 2 copies in Keldysh. I mean, when I mean Keldysh, I mean starting from one SYK coupled to environment and to study real time. You can study this purely imaginary SYKs, 3 of them. That of course you can do it. That is no problem. Technically, you can define Swinger-Dyson equation and you can solve them, but technically it's more complicated. And numerically, SAT diagonalization also is I mean, it's not more complicated, but you have to go to much smaller sizes because you have 3 or 4. So then you go to very small size. That is also problematic.
Yeah, exponentially difficult. More
difficult. Exactly. Masaki-san, exactly. It's exponentially difficult. This is why I wanted to do something like that for years, but I found that it's difficult to do it. I don't want to sacrifice a PhD student on doing that, and maybe then you get something that is not interesting. Or I really need to have some intuition before I start, or something that, okay, maybe you get, it's interesting.
Right.
Yeah.
Actually, I'm also studying three coupled, but Hermitian case. Just in some sense straightforward. Yeah, we are looking for a nice straightforward generalization for essentially, but
okay, that's very interesting.
Yeah, but yeah, if what you explain the Euclidean one for you find for non-Hermitian SYK is essentially different from what we see by directly coupling. then maybe, yeah, to study this non-Hermitian tree coupled with another direction to reach. So yeah.
Yeah, because actually,
yeah,
for non-Hermitian Euclidean, yeah, it makes sense a lot to study the three copies. Actually, I mentioned that to my collaborator Victor, but also he said that it was difficult. He said, no, yeah, we can do that, but it's complicated on gravity. And then I say, oh, an SYK is complicated. Then we start working on something different. Yeah, but it's yeah. In Euclidean, actually, it's interesting project with three boundaries. Yeah, of course, because you can relate that to all these things with Stanford and so. Yeah. In Euclidean, I think is the way to go. Actually, no, in this Kelvin, so in Euclidean, yeah.
Yeah. Say thank you.
Yeah. Okay.
Okay.
Okay. Yeah.
Yeah. Does anyone want to say anything?
Okay. So then again, I mean, thank you very much for the invitation. I look forward to see you soon and
yes.
in person.
Yeah.
Okay. So see you to all of you.
Yeah. So thank you very much, and we are closing the session.